sections, oops, not 11, we're done with that. 12.1 and 12.2 will tell us about double integrals. And I think this section can be a lot of fun if you think of the problems as kind of like puzzles to solve, but people also struggle a lot with this section. So try to really take in these details about what these problems mean so that when you run through lots of practice problems, you can kind of like start building a mental map for yourself about how to solve these. And to start off that mental map, I'd like us to sort of build context for double integrals by thinking about single variable integrals. So double integrals are going to include multiple variables, just like everything in our class has. But you learned how to take integrals in 1D calculus. And just let's think about all the things we knew about integrals back then. They were related to, derivatives, integration, undoes, differentiation. So since we know how to take derivatives in multiple variables, we should expect integration to be really similar to that. You probably arrived at them as limits from Riemann sums. Maybe somebody would have drawn you a picture like this. And you would have said, okay, here's some f of x, and I make a bunch of rectangles. I say, add up the rectangles. In order to get the integral. Maybe you did something like that. Let's actually put bullet points here. And you would have denoted them something like from some number a to b, look at some f of x dx. So for this picture, here would have been a, here would have been b, the bounds of integration over this interval from a to b. And maybe you would have heard like tells area under curve. So after you did a whole bunch of these sums and said, okay, if I take the limit as my rectangles become very, very thin, it's supposed to be the same f of x as before. Sorry that it's different. But here's your bounds of integration. And you would have said the shaded area under the curve is the same value as I get from my integral. Because you're just adding up the heights everywhere along the path for very, very, very skinny rectangles, and that tells you an area. And all this intuition you have about an integral with respect to one variable is going to hold when we start thinking about multiple variables. And so I don't know if you all are familiar with these things, like they're in funny stores sometimes, but it's like this board that has a bunch of pins in it, and if you like stick your hand underneath the board and push it up, then the pins reflect the shape of the hand. And I'm showing you this because I think it's a good demonstration of what a 3D integral does. So let's just imagine here's our y, here's our x, and here's our z. And then what you've done is you've taken your hand, and this is a hand. Okay, there's a shape of a hand that was just pushed up into the board. And I'm going to redraw my axes here. All right, and now when you kind of push up into the board, all this raised region is going to be f of xy. So at every coordinate xy, there's some height z that your hand pushes the pins up. And if you add up the height of all these pins, you'll get the integral. So it's like an approximation of a bunch of, quote, rectangles like you had before, but now it's kind of an approximation of a bunch of pins, a bunch of tiny rectangles. In 2D would be like rectangular prisms is your integral. So let's write some words about that. So we're going to denote them with 2 signs. And we're going to plug in something that depends on 2 variables. Oops. So before, when we took 1D integrals, we had sort of bounds in x, a function that depended on x and integrated with respect to x. Our bounds were this interval. F of x was kind of the height y. Now, f of xy depends on 2 variables, and it's the height depending on x and y, some surface in 3 space. And so we have to integrate over both those variables. So we'll denote that in general. I didn't give myself enough space here. We'll denote that in general as being over some region R integrated with respect to 2 variables dA for kind of area, where it could be dx dy or dy dx, whatever we want to put there, as long as x and y are both involved. And the region R, oops, gotta switch back to my color, is like the shadow that we push into the plane to create our surface. So when I stick a hand up against this pin board, that's my region R. And then when I push it up, my integral is the sum of the height of all the pins when my hand is in the board. If none of you all have seen these pin boards before, this is going to seem like a really pointless example, but it's the most hands-on you can ever get with a 2D integral. And so this is how we denote a multivariable integral. And instead, what it's going to tell us is volume, under a surface instead of area under curve for f of xy over some region R. So this rectangle thing, Riemann sums, we showed with our pin board. We showed the new way to denote an integral is really similar to what we had before, just written for 2 variables. And then this intuition you have about area under curve, we're doing exactly the same thing. We say when we calculate this integral, we get the volume under the surface, how much space there is underneath my hand when I push up all those pins over some shadow in the xy plane. And then for now, I'll just tell you that we take integrals as antiderivatives treating each variable separately. Just like how we treated partial derivatives separately, we're going to do the same thing where we say when we're integrating with respect to x, we treat y constant. Integrating with respect to y, we treat x constant. And so, let me check the time. Okay, so in the next video, we'll go ahead and talk through the steps that you actually take to solve one of these problems.